morning to everyone. First of all, my name is Elizabeth Diego Navarro. I am a member of the board of ECUSA-NY. Before starting with the presentation, I want to give you a brief introduction of what are the objectives and the main activities that our association is doing in New York. So we have three main objectives. First of all, ECUSA-NY aims to establish a professional scientific network in the US, and we are doing that through networking events. Also, we try to increase the public awareness of science and technology. We want to do that by making this type of science outreach events. And we want to facilitate the interaction between public and private institutions here in the US and in Spain. So in the brief period that ECUSA has been going on, we have reached to great achievements. We are more than 500 members, and we have a significant media coverage as our event where we present the association in New York. We are the connection point between American, European, and Spanish institutions. For example, with CEU University, we are developing a program for exchange students from Spain coming to the US. We are a link between American and Spanish scientific professionals. In ECUSA New York, we have five main groups of working. The first one is science outreach. And in this group, we are developing like the conference rounds like this one. And this is the third one that we are doing in the Instituto Cervantes, and we are preparing the next three for the autumn and the summer session. We are working in the program. Also, we want to organize visits to the American Museum of Natural History, and we want to collaborate with the Spanish visiting students that are coming here in New York for the summer or to study, to establish collaborations with them. In the advisory committee, we are doing the welcome package. This package will be like a guide where we will present information useful for graduate or undergraduate or postgraduate students that are coming to work to the US with advice in visa types, living costs, all of that. And also we are in active negotiation with institutions to organize informative sessions about taxes that could be of great interest of professionals working in the US. In the networking area, we held our first event of networking on the March 13, and we are working in the next rounds. In professional development, and also, we are preparing a new program that is called Fostering Docs. In this program, it would be senior professionals would mentor graduate students of the last year and postdoctoral that aim to go forward in their careers. In the professional development, we held the first Beyond the Bench event at the beginning of this month in La Nacional. And this event was an informative session about other non-academic professionals that were showing how their new work was carried out. And it was a great success, and we had a lot of attendance. And in the institutional relationships group, they are in charge of developing new links between institutions. And if you are not convinced why you have to become a member, these are other reasons. So you will belong to our scientific professional network. You will have access to information about events, resources, and job offers. And also you will have opportunities to expand your scientific professional skills with workshops that we are programming. And also, you can suggest, organize, or attend other events with ECUSA. How to become a member is easy. You just have to go to our webpage, that is www.ecusa.es, and there in home you have the become a member. Also, you can come to us and we will fill the forms for subscription to ECUSA. And lastly, you can follow us in Facebook, LinkedIn, and Twitter. And if you have any suggestions, proposals, or collaborations, you can just contact us on our email, newyork@ecusa.es. And now I will introduce to my colleague, that is Adrián Soto, that is going to present our speaker.
Thank you very much, Ellie, for the very nice overview of the stuff that we're doing in the association. I want to start briefly by just thanking the people who are making this possible. The Ramon Areces Foundation is funding this program, and we're also having support from the Foundation for Spanish Science and Technology, as well as the Embassy of Spain. And of course, the Instituto Cervantes is very kind in letting us use their facilities for today's event, so we're thankful to them too. I'm a physicist, and I read in the news today something that I feel very proud of as a physicist, even though I do something totally different. Yesterday, it was a great scientific achievement, yet not yet a discovery though. At CERN, at the Institute for or the European Organization for Nuclear and Particle Physics, they managed to have the first collision between two protons, these tiny particles that make up matter, at the highest energy ever achieved by a human-built machine, an energy of 14 teraelectronvolts. That's way too high an energy. Today we're going to be talking about energies about 1,000 billion, I think, and like 1 trillion times smaller than that in the order of an electron volt. Billion times, sorry. Billion times smaller than that. But let me introduce Emilio. He's a native of Spain. He was born in Catalonia, and then soon after that he moved to Madrid, where he attended school and also university studies at the Autonomous University. He has an interesting story because he's an almost double PhD scientist. He was almost done with his PhD in Spain. He had an opportunity to go do some experiments in Cardiff in the UK. And then when he was about to finish, he threw it all out the window and he decided to go to Massachusetts Institute of Technology to start over his PhD. And then he did over there a PhD in physics. And then started in 1974, if I'm not mistaken, and it took 5 years. Then soon after that, he was hired at IBM Watson in upstate New York, where he was a postdoc for 1.5 years, and then staff member for 15 years, if I got that right. And then after having worked there, being a group leader at IBM Watson, he had an opportunity to become a university professor. So he moved to Stony Brook, so from upstate to Long Island, to join the Department of Physics and Astronomy, where he still is a professor of physics there since 1996, in condensed matter physics. And a few years after that, he also took an active role at the Brookhaven National Lab, where he's now the director of the Center for Functional Nanomaterials. And today we're going to be hearing very interesting stories about the work that they're doing there and other things related to nanotechnology. So please join me to welcome Emilio today.
I feel like in a comedy club. I'm completely blind. I don't know who you are. So let me start by asking you a question. Who among the audience is a scientist? Good. At least 50% are not scientists. Great. Who of those scientists is a physicist? Only two. Even better. Okay. There are too many physicists in the world anyway, so we don't need to know. Can you hear me well?
Yes.
Okay, thank you. So yes, I almost threw away a full thesis and started a new one at MIT. So I finished my degree when I was 30 years old, and I don't know what is a better achievement, either to do a PhD at MIT, or to do it with 2 daughters. I started just the first year of being a graduate student with 1 daughter, and then 2 years later I got the second one. So I think the big accomplishment is probably not myself, but my wife was able to grow, or raise 2 daughters, and at the same time be able to cope with myself and my thesis. Today I'm going to talk about something entirely different, and nothing to do with my life, nothing to do with the kind of research myself I do at the university, but rather it's a very interesting story, that a very interesting career that we started a number of years ago. So I decided to use a theme which is extremely long, and I will try to focus it onto a number of elements associated with very, very important challenges that we have. A challenge that we call it the energy challenge, and how nanotechnology can address, at least partially, the challenge presented by energy. So my talk essentially going to first tell you what the challenge as I see it, the energy challenge is. Second, I will tell you what nanotechnology is. And third, I will tell you how nanotechnology is helping alleviate, mitigate the energy problem. So let me start first by saying something about the energy problem. Well, the challenge is the following: trying to answer this question. How can a crowded world keep growing on a blue planet? Emphasizing 3 things. Crowded world, we are 7 billion people, 7,000 million people. Growing, that you are going to see growing in all, not only in the number of people, but in the energy that we consume. And also keep it blue, meaning keeping livable. It's a big challenge. It's a big challenge because we essentially depend on energy to be able to make this possible. But energy is a very tricky issue. It's a very fragile issue. Actually, if you ask a physicist what energy is, if he's really honest, he will say he doesn't understand. If some of you who are physicists, you remember the Feynman lectures in physics, look for the definition of energy. You will see how interesting that he's saying energy is something that we put at the end of an equation, so we make the left-hand side equal to the right-hand side. But I will discuss this in a different way. So energy is a very, very fragile issue because we depend, to a very large extent you are going to see, depend on fossil energy. Essentially, we depend on oil to a very large extent. And oil is, first of all, is finite, also is not evenly distributed through the world. Therefore, the price of oil, the chemical price, of course, to coal and natural gas, but mostly to oil, the price of oil goes up and down. This is just the price of the barrel of oil through the years. At one point, not many years ago, it was close to $150. You have to fill your tank, and if you have a small car like mine, you spend $35. If you have a big SUV, you spend $70. Now, of course, the price is relatively small, lower compared to this. Now it's about $55. Still, the price goes up and down, and is very unevenly distributed through the world. This is why there is so much geopolitical turmoil associated with oil. So these are finite resources, not equally distributed. But equally important, probably more important, is in the long run, is because we depend so much on fossil fuels, this is affecting significantly climate change. This is another talk, and if you are interested, other day I can come back and tell you about the connection between climate and energy, a very interesting discussion. I will not spend too much time on this today. But yes, I want to talk about energy and how energy and economic development are intimately related. Let's look at this view graph. Here, on the left, on the upper side, I'm showing the energy consumption per person in megawatts hour. Okay? A unit of energy, let's call it this way. On the right hand side, here, I'm talking about the GPD, the gross domestic product per person. You can see a very strong correlation between the economic development and the energy consumed per person. Let's take the case of South Korea, for instance. You can see the GDP per person has increased from wherever it was to something like $15,000, and the amount of energy consumed has increased linearly with that part. This applies especially to most of the developing countries, not so much so for the US, in which the amount of energy consumed per person have remained constant, even though the GDP per person has doubled in the last 15 years or so. I leave as an exercise for you to try to explain this trend as compared to the other one. And we can talk about this in the question and answer period. On the average, the world has a GDP per person of about $10,000 and consumes per year 10 megawatt per hour. Imagine when China and India and other emerging countries are going to go from here up there. Keep in mind that this is per person. Keep in mind also that in China there are 1.3 billion people, that in India there are close to 1 billion people, and they are increases. So when you compound this situation with the explosion in population, now we're about 7 billion, by 2050, the consumption of energy can only increase significantly in the next 5 years. This is an economic fact. So no matter what you do, no matter how much vision, this is the reality. If we want the world, and we want the world to move in this particular direction, the amount of energy per person is going to increase 3 or 4 or 5 times. Multiply this by the multiplier in population, you will see the huge increase in energy. Energy comes from somewhere. Where is it coming from? So this shows in some unit, equivalent of all barrels of oil, is a function of time, the consumption of energy of the different kinds. You can see coal, oil, and gas take the lion's share of the consumption now, and it will remain the same at least for the next 20, if not 50 years. So this is the reality based on this type of projection. Keep in mind that yes, there are some other important renewable, as we call it, doesn't depend on carbon to produce energy, but these are small fractions, and the fraction will not increase much more. The amount will increase, but the fraction will not increase significantly. So the reality is that we depend on these 3 hydrocarbons, coal, oil, and gas, hydrocarbon or carbon related, and this is going to remain as it is now, more or less for the next 30 years. The implications for climate are enormous, tremendous, and frightening. As I said, it will be a talk in itself, I'm not going to spend it here. So this is the challenge that we are facing. How to, with an increasing production of energy necessary for economic development, we can have it in such a way that we maintain the planet as a blue planet, that we used to call it in the 1980s back in Spain. Okay? So the big challenge. So how to approach the challenge? Well, the approach is to be mixed. It's completely naive and what is the word I'm looking for? But completely naive to think that we can change overnight to renewable energy sources. We have to maintain, this is the reality, we have to maintain other energy sources. Could be nuclear, could be oil, could be gas, could be coal and so on. Naturally trying to reduce as much as possible what we call the carbon footprint. So this is the first thing that comes to mind when you think how to answer, how to reduce as much as possible the consumption of energy, and mostly the source of energy which is coming from carbon related. First of all, use less energy. Increase the efficiency of existing gadgets, and I will say something about this later. And also develop new gadgets that are much more efficient in terms of the energy consumption. Again, I will say something at the very end of this part. Make the processes much more efficient. We are going to talk about a chemical process called catalysis. Catalysis is a tremendous enhancer of reactions, therefore produces much more stuff, but it comes at the expense of a lot of energy produced or necessary to produce, for instance, ammonia. 3% of the energy consumed in the world goes in the production of ammonia. It's mostly used for fertilizers and other things. Okay? So finding better catalysts will reduce significantly the amount of energy that we use. This is what I mean by more efficient processes. The other thing which is crucial is to alter the mix between different fossil fuels. We've seen, read about it, the large increase in the production of natural gas in the United States, because through freight and so on. So this is altering already the equation. You are seeing how much the United States is becoming independent in terms of energy. Oil, the production has increased 30%, but also natural gas. This automatically is important enormous geopolitical, not only, but also economical consequences. So altering this mix is fundamental, is critical. Electrified transportation, 30% of the consumption of energy goes into transportation. Okay? Electrifying is essential, we are going to talk about this later, how to change the gasoline model that we have into something, into electric car, and what is the challenge that we face in there. Sequester greenhouse gases. No matter what, we are producing CO2, both in the production of electricity, other things. Capturing CO2 is fundamental to reduce the amount of CO2 in the atmosphere, which is about 400 parts per billion right now. And finally, ultimately, the only solution in the long run is to develop new sources of energy that are completely inexhaustible. Something essentially comes from the sun. Ultimately, all the energy that we have on the earth is coming from the sun. Find a way of absorbing the energy of the sun and using this as possible the only source of energy. It's the only solution in the long run. But in the meantime, we have to work with all the other alternatives. So today, I'm going to tell you, as I said, how nanotechnology is addressing some of these issues with some examples of them. But the main thing to keep in mind is how much energy is wasted in the processes that we are doing through life. So the first thing is reduce the amount of energy they are wasting. Energy is basically wasted in the form of heat most of the time. So in the case, for instance, I'm going to give you an example later, 66% of the energy created is lost in electricity, in the production and the distribution. You will see an example, as I said. In the case of transportation, 71% of the energy is lost in the form of heat. I have to say that some of this energy being lost, it be lost because of fundamental physical reasons. There's something called the thermodynamics, the first and second law of thermodynamics and Carnot cycle, that tell you that no matter how efficient an engine is, you cannot have 100% efficiency. But still, we have not reached the fundamental limit set by physics. And clearly, in industry as well, in buildings, a significant amount of energy is lost. So the first thing is to reduce the losses to make something much more efficient. Now, why nanotechnology? Where does it come? What makes nanotechnology different from other technologies that came around before the last 20 years or so? Or how nanotechnology can contribute to address, to solve, at least to alleviate, to mitigate the energy problem? For three main reasons, some of them quite trivial. One, which is the most basic, the most fundamental one, the deeper one, is on a nanoscale. And first I have to define what a nanoscale means. Nanoscale, I mean the following. In mathematical terms, a nanometer is 10 to the minus 9 meters, or 1 billion in American units, or 1,000 of a million of a meter, or 1 millionth of a meter. And to make it more understandable for a non-scientist, here I would say you have one and you can afford it. Take one hair on your head and look at it, and you will see that the width of your head is the hair of your head is about 50 microns. It means that you look at the width of your hair, you can put 50,000 nanometers across the width of your hair. 50,000 nanometers. So very, very, very important unit. And still we are going to look at properties, dimensions, objects at this particular scale. Now, why nanoscience and what is different on the scale? So I say for those who are physicists in the audience, for those who are scientists, you remember, well, physicists have to use it every day. Other people remember from high school, quantum mechanics. At the nanoscale, at that particular scale in length, things behave different. We are used to the idea, based on chemistry, that different materials behave differently because they're different atoms, different composition. For instance, there are different colors in here because there are different pigments, each of them within particular kind of chemicals. Different colors, different compounds. In reality, when you look at this minuscule scale, at the nanoscale, geometry matters as much as composition. Let me give you an example. Take a look to this set of flasks, going from the deep dark to the deep blue. The material inside is exactly the same in all of them. It's a solution, an organic solution of a material that we call it cadmium telluride, a material made out of two different elements. It's exactly the same material in all of them. However, the light emitted, the fluorescence of that material is different from the left blue to the red on the right hand side. The only difference between, or among I should say, this flash is that the size of the particles under which or in which this solution is made is different. In one end, I don't tell you which one, the particles are the smallest. On the other end, the particles are the largest. The question is, and only non-scientists are allowed to answer, on what end are we talking about? On what end are the particles contained in the solution the smallest? On the left or on the right? The 50% chance of winning. You can volunteer and answer. Come on. Yes.
For left side, small particle.
So you're saying on the left-hand side are the smallest particles. By the way, these particles are the order of 20 nanometers, maybe 50,000 in the width of your hair, from 20 nanometers to 5 nanometers. So you are saying the smallest particles are on the left-hand side. Therefore, the biggest particles are on the right-hand side, on the right. Why is that? What made you think that way?
For the particle in the box, we can.
So you might be a physicist, come on. You are disqualified. You know too much about it. That's exactly right. But let me give you another example. Think of a musical instrument. Think of a cello and a violin. Which of the two instruments produces the highest pitch? The violin. Conversely, which of the two instruments produces waves, sound waves, with the longest wavelength? The cello. Typically, big people, bulky people have a very deep voice. Little birds have a very high-pitched voice. The same applies in here, that the particles with the smallest size produce, if you will, light with the highest frequency, like the tiny birds. Whereas particles with the largest size, like cello, produce light with the largest wavelength, the higher, the lower frequency. Okay? Now, you will say, what is the connection between sound and light? Ask this guy who knows how to Anyway, so the main characteristic of particles at this scale is that they behave differently. I'm talking about an example here, color. But you can say the same about transport property, meaning conductivity of light or current, or magnetism, magnetic property. They depend on the size of the material. So you can just tune the properties you want just by making the particles or the object smaller or larger. First problem. The second one is very interesting for catalysis, for the chemistry part of the story. Why? Because in many cases, reactions take place on the surface of a material. And the smallest the size, the largest the frequency. The larger the surface, relatively speaking. Let me give you an example to try to illustrate. Suppose that you take one block, 1 cube of sugar, like the one that we used to put on the coffee first, right? If a 1 cubic centimeter, 1 cube of 1 centimeter on the side of sugar, that has a certain volume, 1 cubic centimeter, and a certain surface, 6 square centimeters probably, right? Now you take the same cube and just break it into tiny little crumbs. The total volume in aggregate, does it change or not? It remains the same. The volume does not change. But the total surface, the aggregate surface of all the little particles has increased dramatically. So by making particles or objects smaller, the surface plays a much larger role than in larger objects. This is why catalysis fundamentally is nanocatalysis, because at the nanoscale, the surface has an enormous contribution. You can make much more surface with tiny particles than with large particles. Okay? The third one is even, the third one is even more obvious, which is something which is In Spanish we say perogrullo. The nanoparticles reach everywhere, meaning the particles are very, very tiny. They're able to go through parts of the organism they couldn't go otherwise. This allows us, for instance, to direct object particles with interesting properties that we can control into different organs of our body, therefore control what's going on or serve as a sensor for something going on. So it can serve either for diagnosis or for healing some ailments. And I know there are some medical doctors in the audience here, and some of them may be already applying this type of techniques, for instance, to pinpoint location of tumors, curing tumors, and so on. Today I will be not talking about this part, naturally, but I will talk a little bit about these two parts. So now, let me descend into nanotechnology, where we do this. This is being done, in our case, it's being done in a center, a relatively small center, only 65 people, within a larger laboratory, at Brookhaven National Laboratory. I wanted, but didn't find time to identify, to locate where in New York our center is. It's on Long Island, on the way to the Hamptons, but before you go to the narrow end, turn left on exit 62, continue 2 more miles, turn right, leave Brookhaven National Laboratories, about 60 miles from here. So we are part of the Department of Energy, and we are one of the 5 nanocenters that the Department of Energy put together around 2005 to try to address, from the nanotechnology point of view, the energy challenge. There are other centers in other parts of the country, you can see, more or less distributed through main corridors where science and technology is quite strong. So we have, interesting enough, a double mission in our center. One is, as I said, this will be another talk in itself, to do our own research, the one I'm referring to here, but at the same time, it's part of our mission to serve as a resource for users from all over the world who come free of charge to do research in our wonderful facilities. It's a national treasure, I would say, an international treasure. We have now more than 470 users who come from all parts of the United States and also from different parts of the world who come to do research in our facilities. It's our mission to train them, to help them do their own research. And in some cases, we collaborate with them when the interest is relatively common. I will not spend much time on this, but it's important for you to know. It's a great service. And when we were coming on the subway, we were talking about this, and again, this is another talk in itself for another day. So now, the facility that we have at the center refer to the 3 main characteristics that you can think of nanotechnology. You're thinking of creating particles, for instance, at this scale. You can make rods, or you can make tubes, you can make circles at the nanoscale. The first thing you have to synthesize the materials. You can just either create them with chemical means, meaning a chemical reaction, or you can just do patterning, as we call it, with what we call electron beams to make the particles, chopping them into very, very tiny areas. So this will be called synthesis and fabrication. Then we characterize those materials that we have built, or our users can build with us. We characterize them with very advanced tools. Some use electrons to see, what we call transmission electron microscope. There are going to examples of those things. And sometimes we look with photons, meaning with light, but not only visible light, many times with X-rays, for instance. So we are part of a complex in the laboratory. We have access to the strongest, to the brightest, what we call synchrotron radiation accelerator in the world for X-rays. It's a brand new. So very, very fancy tools. Actually, we have invested in those tools close to $40 million already. Okay? That center, when it was created, cost $80 million. With a budget of about $20 million, we've invested 39, close to $40 million. Now, what do we do there? So first, let's talk about efficiency and bring out the idea of efficiency and how inefficient the electric grid is. Consider, for instance, what it takes to use your light bulb. Okay? So you start here, this is a coal plant, with 100 units of energy, whatever the unit is. Could be calories, could be whatever you want to do. Okay? You start with 100 units. Now, in the production of the electricity, you lose 62%. A very inefficient process. From 100 you go to 62. You create electricity, but now you have to transmit it from the higher station all the way to your home. But in the process, they're also losing a significant amount of line, actually 38 units in the transmission line. Okay? That when it enters in the transmission line, the conversion from here to transmission, you lose significant fraction. In the transmission itself, you lose another 7%, which is about, in this case, 2 units. So by the time it gets to your home, with only 36 units left. You plug in the light bulb, you lose most of it, so at the very end, only 2 units of energy are being used. Most of the energy of a light bulb, it goes into heat. Very inefficient process. Of course, we've known this for many years, the technology more than 100 years old, and then we developed the fluorescent light. Actually, this is the pace taking humanity to go from the oil lamp to the LED. I was reading one day that it took 47 hours of labor for a person to be able to buy the oil that could be producing the amount of light of a light bulb. 47 hours of labor. When the light bulb was created, from 47 hours became 4 minutes. Now it's much, much less than 4 seconds. So efficiency has increased enormously. The big jump is now what we call the LEDs. Because before, to produce 300 lumens, and to be generated, a typical light bulb produce 1,000 lumens. To produce 300, now only 1 watt is needed. With the conventional light bulb, in order with 1 watt, we can only achieve 16 lumens. Significant fraction, about a factor of 20 in gain in efficiency. No wonder that the Nobel Prize in 2014 was awarded to the work that made possible these LEDs. This is a very clear example of nanotechnology in your LEDs. In order to produce these materials so efficient, this is something called light emitting diode, you need to produce with exquisite thickness control these many layers of different materials or different compounds. Some of them as narrow as 2 or 3 nanometers. So it requires a lot of technology for that part. This is something actually was part of the kind of work I've been doing through the years, first at IBM, then at Stony Brook myself, but I will not linger on that part. Let me talk instead of the kind of work, examples of that we are doing at our center in Brookhaven National Laboratory. Let's talk about batteries for a while. I'm going to focus on 3 examples: batteries, fuel cells, and catalysis. Let's start with batteries. I'm showing here, on the right-hand side, the amount of energy that you can store per gram. So the deal is essentially to store as much energy as possible and make it as light as possible. Is the idea, right? Actually, I've been using a prehistoric cell phone until last week. I was extremely happy with them, extremely happy. Light, efficient, and the laboratory decided I should be upgraded, and they gave me what I call a brick phone. A wonderful phone, 5 inches side on diagonal, but it weighs like a brick. A significant fraction of the energy, or the weight is probably coming from the battery. Not only that, every night I have to plug it in and keep it plugged in for 8 or 9 hours. So clearly the goal is to have as much energy stored in as little space or little weight as possible. So this is, on the other hand, you want this to be stored, but at the same time you want to deliver this energy as quickly as possible, especially if you have to run something very quickly. You want to accelerate a car, so you not only want a lot of energy, but a lot of power, meaning delivers a lot of energy very, very quickly. So these are the 2 coordinates on the scale. So for instance, batteries, like lead-acid battery, the one that we still have in our regular car, is able to store, depending on the circumstances, the order of 4 watt-hour per kilogram. Okay, it's in here. It took about 200 years to be able to go from this type of batteries to the lithium-ion battery. It was able to increase by less than an order of magnitude. It took 200 years to be able to go to the kind of batteries that we are using now in our beautiful cell phone. And now they are being used in electric cars. But in order to have a true electric car in a meaningful way, meaningful is relatively inexpensive, runs for 250 miles, and is not very heavy, you need to have a higher battery storage. You have to have something relatively fast, so it's a very pretty car. At the same time, you have to have enough energy. So there's plenty of room here to grow. So we have to accelerate the 200 years into something much faster. So this is the challenge regarding batteries. For the other type of energy storage devices, like capacitors, in which the amount of energy that you store is not so great, but on the other hand, you deliver the energy very, very fast. So ideally, you would like to have a combination of the two, battery energy and capacitor power. So let's talk quickly about lithium-ion batteries. So battery is relatively simple stuff, essentially consists of two electrodes, something we call the negative, something called the positive, the anode and the cathode. In the case of the lithium-ion batteries, the anode, which I'm going to focus, is essentially graphite. Why graphite? Because what you do is just to take the lithium, thereby the name, lithium, and you put lithium in the layers of graphite. And the more you put in there, the better, because you store store much more energy. Then in the recharging process, you move the lithium from here. You move the lithium, and therefore you generate some current in the process. So the name of the game is exactly to find what is the best material that stores the most amount of energy in the least amount of space without problems. Because lithium-ion battery have a number of problems. One is, you want to say, capacity. You like to store more energy, so you have to recharge it so often. You like to have it lighter, so I don't have to go like this when I'm wearing my cell phone. You have to make it stable, and you have to make it safe. At the same time, of course, you have to reduce the price. So these are the challenges associated with batteries. Now, interesting enough, graphite is not the best material for an anode. There are much better materials. For instance, tin, or germanium, or even better, silicon. These are much better materials than graphite. The question is why people don't use battery made out of silicon or made out of tin. For a simple reason. You're able to store more into those anodes, more lithium. But when you store more, the volume of your anode changes, increases significantly. And when you discharge, decrease the volume. So this increase and decrease of volume make the system very short-lived. There's so much mechanical tension, basically the system breaks. So these are one of the big problems of being able to use other much better ideal material. So this is how we solve the problem at BNL. So rather than having regular silicon, what we do, we put for the anode wires of silicon. Not only that, wires of silicon, there are plenty of holes, plenty of pores on the side of the wires. So there are pores, very tiny, the order of 5 nanometers. So that when you charge the anode, the lithium goes into the holes, goes into the pores, therefore the volume doesn't change much. So you can sustain up and down, opening and closing the number of cycles that you can have. So this allows us, actually, you can see here as a comparison, graphite, this is the amount of capacity, the amount of energy that you can store per unit gram. But if you do these nanowires and you disperse some carbon black to increase the conductivity of the material, the capacity, the amount of energy stored is much better. If you do the same thing, but put in there some solution or some powder of graphene, it's another form of graphite, then the capacity enormously increases. You can see a big increase in the amount of energy simply by changing the material, being ingenious enough, and creating wires, narrow, very dense, and full of holes and pores where the lithium ions can be stored. Good example of how nanotechnology can help make batteries which are much better than the existing ones. But people are talking about not only about the regular batteries for cars, also it's a big competitor in the new direction of cars. In fact, Toyota is investing very, very heavily in this type of fuel cells. Cars in which rather than having a regular battery, you have a fuel cell. What is a fuel cell? It's nothing but a fancy kind of battery which rather than having these compounds, you have something very simple. On one hand, you have hydrogen, and on the other hand, on the other side, you have oxygen, air. You put together hydrogen and oxygen, and you create water. You are able to separate the charge, therefore here you put positive charge, and here you put negative charge, exactly as in the battery. The advantage is that you don't need any other thing inside except for having hydrogen and coming here with air. So very simple stuff. You have a cylinder with hydrogen, you make it some kind of reaction vessel, you make it air coming in, you produce water as byproduct. As a result, you create like a battery. You can just put a lamp, therefore you can create electricity. There is only one problem, there are two problems. One problem is you put hydrogen and oxygen spontaneously, naturally, they don't form water. You need to activate that reaction, you need to catalyze. So the first thing you need to have this thing possible, we call a catalyst. And second, you have to find a good source of hydrogen. Hydrogen is not existing freely, you have to find a way to do it. So let's address two things. First, the catalyst, and second, the source of hydrogen. Regarding the catalyst, we have been working with our colleagues in the chemistry department, with companies like Toyota, for instance, and trying to address the question is, what will be the best, the cheapest, the most efficient catalyst? The catalyst they typically use, and you have seen also in your catalytic converters in cars, is platinum. Platinum has two problems. One is very expensive, and secondly, it gets contaminated, it gets poisoned, and when used with CO. So let's address the question of price. As I told you before, all these catalysts, what really matters is the surface, not the interior. So why the expense of putting the entire particle made of platinum, what really matters is only the exterior part? Why not use inside what we call fodder material, something which is inert, only to provide the bulk, and just have only in the periphery expensive material, platinum. And this is what our colleagues in the chemistry department did. They created, through chemical reaction, a material that on the inside was palladium, and more recently nickel, which is relatively inexpensive. And on the outside of this particle, this here is a simplified model, it's like a hexagon, is platinum. But the question they have is, how do we know that what we thought is palladium and platinum indeed is such a thing? So they came to us and said, why don't we look with the microscope that you have, use electrons, what we call transmission electron microscope, is able to identify individual atoms and see indeed what you have. So this is what we saw. This is a picture, it's relatively amplified but not that much. This is a matrix in here of carbon, just the holder, you will, and these are the individual particles that we thought it were palladium, and on the outside, in the shell, will be platinum. So what we did, we increased the magnification. This is the type of microscope they want us to use, and we'll come back to this in a minute. We increased the magnification, and we were able to see individual atoms. So these are individual atoms seen by this type of microscope. The microscope is one of a kind in the world. It's extremely, extremely high resolution, requires a huge stability. This is why the scientists are outside the room, the instrument inside, because the stability in temperature is paramount to the stability instrument. The body temperature is enough if you go into the room to change the alignment of such a microscope. This is we have to mount the sample, get out, spend a couple of hours, stabilizing the temperature, and then you do the experiment. The stability in temperature is better than 0.1 degrees in 24-hour period, an enormous stability. Of course, mechanical stability matters, so that this is isolated in a big, thick, 2 feet concrete of lateral concrete. And here also there is electromagnetic isolation to be able to produce this type of stability. So here we're able to see individual atoms. But the question is, how do we know that indeed some of these are palladium and some of them are platinum? We have to rely on a technique that we call EELS, energy electron loss spectroscopy. Essentially, it's like looking at the reflection of different materials. This material that reflects yellow, and we know this type of pigment. this material reflects red, we know this type of pigment. So now we look at the scattered electrons, if you will, from the reflection of these atoms, and by the spectrum, if you will, as we call it, by the spectrum we can identify that in the core, inside, with indeed palladium, and outside we have platinum. The most important thing is that the efficiency of this catalyst is even better, and certainly much more better when we consider per unit weight than the conventional platinum. It's another way for really decreasing the dependence on materials to be able to produce the same result. The efficiency increases at a much lower price. We can do this because of the chemistry and also the kind of instrument that allow us to see at the individual atoms. Now, I talked about, when I was talking about fuel cells, I said there are two main issues. One is the catalyst that make the reaction possible, and the second is, where is the hydrogen coming from? The hydrogen is coming from water. And we will learn when we are in elementary school, so you can have something called electrolysis, right? Where you put water, you put some sulfuric acid, or some salt, you put two electrodes, put a battery, and basically you can see bubbling there because you are producing hydrogen oxygen. A great way of producing hydrogen. But keep in mind that the goal is to produce energy to run cars. In order to produce energy to run cars, you need hydrogen. But in order to produce hydrogen, you need electricity. Therefore, you need to go back to the power station and start with coal. So you are not solved the problem. Another way of addressing the issue is by looking at chemically formed hydrogen. This is through a reaction. You start with methane, you just produce a reaction with some catalyst, eventually you get hydrogen. But this also consumes energy in the production. The best way would be, if we could do it, is start with water. If we were able to split water not with electricity but with sunlight, then we have the best of both worlds. Because we start with water, sunlight, in a miraculous, mysterious way, will be able to produce hydrogen, with this hydrogen to produce the fuel cells that run on our cars. So the question is, how do we make sunlight to break hydrogen and water into hydrogen and oxygen? This is something that will happen spontaneously. When it rains, you see a pool of water, the water stays there. You don't see this becoming spontaneously into hydrogen and oxygen. Once more, you need something to activate the reaction. You need what we call a catalyst. A catalyst that actually works under the influence of light. We call it a photocatalyst. There are a number of those. The photocatalyst, for instance, is titanium oxide, titanium. The problem with titanium is the following. It absorbs mostly ultraviolet light. And the sun primarily emits light into the visible. So we will need a material, a catalyst, that absorbs light in the visible. And for the moment, there is none. So in our laboratory, we are working with some compounds, and you may be familiar with some of these. We are working with a compound which is a mixture of what we call gallium nitride, actually the material in which those blue lights were created to produce the LEDs, gallium nitride and zinc oxide. We are making nanowires, extremely narrow, extremely long, very uniform, and these are promising because they can absorb light into the visible part of the spectrum, and now we are testing how reactive they are, how much they can convert water into hydrogen and oxygen. Another example of how nanotechnology is allowing to alleviate the energy problem. The third example I want to talk about is efficiency once more. You are very familiar with solar cells. As I said, the ultimate goal is to get the sun's light, capture the energy, convert it, store it, and use it. We are talking about solar cells. Solar cells make a big change in the last 10 years or so. Actually, I could have shown you the trend that we have seen 8 years ago, how the trend in price has completely broken all the expectations that have been drastically lowered the price than we expected. Still, they are not as efficient as they could be. For instance, when you are making these solar cells, part of the light is reflected back. Silicon reflects part of the light. the interesting will be able to absorb all the light, so all the light will be converted into energy in the form of electricity. The problem again, some of the light is reflected. So we developed a technique at our center, at the Brookhaven National Laboratory, in which the amount of light that can be absorbed by creating this forest of nanoparticles, all of them identical, in very large surfaces, the efficiency increases drastically. All the light actually is absorbed. You can see here is an example. Here you can see a reflection of this picture onto this silicon surface, but in here we have put in front of it, we have put a piece of this anti-reflecting material, completely black, and the size is comparable to the quarter of a dollar. So we can create structures which are so uniform, so dense, that the energy goes inside, the light goes inside, is trapped, basically cannot go out, and we can just use all the light to convert it into electricity. Very interesting, because this process we are using now for something entirely different. Actually, to create the same idea by using this to create surfaces which are hydrophobic. Therefore, they repel water. So if you have a surface like this, it doesn't wet. Therefore, the light, the water is reflected. Imagine what it could be done, for instance, for the windshields or for some engines of airplanes. Therefore, they are not get wet in a particular way because all the water is reflected. It's interesting. I was talking about this a few days ago with somebody who is the director in Qatar of a big energy center. So one problem that we have, we are using plenty of solar cells, but one of the problems we are facing is that in Qatar, in the Middle East, it's very sandy, it's very dusty. So all the solar cells very quickly are coated with a thin layer of dust. Could we use perhaps this technology to make anti-dust surfaces? And I don't have the answer, but we are trying just in case. It's very interesting because this person came to me, when was it? Last Monday. A week earlier, I got a message from another colleague, a former director of the laboratory. So, Emilio, I've been in Africa and I have a problem. I have a problem because I was visiting this particular center and I discovered that they're wasting so much time in the following. They're depending on solar energy. But it's so dusty there that a person at the end of the day has to go and put some water to clean, and then they have to basically sweep all the dust away. They're wasting so much energy, so much manpower. Can you find ways of addressing this problem? Two different people, one from Africa, one from the Middle East, with the same kind of issue coming almost at the same time. So now we are trying. We are just putting a graduate student to work on this problem. Can we create, well, rather than sweeping, something much more effective, which is basically a graduate student to try to address with high technology. So let me give you another example of how in science sometimes things that we think in one particular direction can have applications in many different parts that we didn't think initially, only with interaction, with collaboration, and talking to each other, something that ECUSA is trying to foment. I'm going to skip this part, I believe. But this is a fascinating field we're also working. Let me give you a couple of ideas, which is mixing biology, I know that some of you are biologists, with nanoparticles. What we are doing in the following, we are what we call functionalizing, in plain language terms, we are coating some of the nanoparticles with DNA. Well, we're using some particles with one strand of DNA, another type of nanoparticle with different strands of DNA. You know the two strands tend to tie together. So what we are doing is we are using DNA to link different particles or different type of nanoparticles. In this particular case, this is a gold nanoparticle, and this is another material we call a quantum dot, a very tiny thing that emits light. We want the light emitted to be as bright as possible. It turns out, as physics tells us, according to plasmonic effect, that you put this gold nanoparticle as a metal close to this other particle, the light emitted by this tiny little thing can be enhanced drastically. But it's very, very finicky. It requires the distance to be exactly one, like the three little bears, not too large, Not too small, just the right size, and also the same for the size of this particle. So by linking these particles with DNA strand, we're able to enhance significantly, orders of magnitude sometimes, the amount of light produced by these materials. It turns out that we are able not to make this type of pair to material. Now we've been able to create something we didn't expect at the beginning, create new materials in which we can create crystals, but not sodium and chloride we normally see in the textbook, but rather at the edges of the cube, we are seeing nanoparticle themselves. So we are creating super lattices of nanoparticles with entirely new properties, optical, magnetic, and chemical properties. It's a very fascinating field that we are now pioneers in this. We don't know where it's leading, but certainly it's very, very, very interesting. I'm going to finish by saying a few words about efficiency, and this will be a lecture in itself. Just to try to caution about increasing the efficiency. Let's look, for instance, at refrigerators. Here, I'm showing three things. First of all, I'm showing here, starting in 1972, the amount of energy spent for the typical refrigerator. Same capacity and then everything. The amount of energy will reduce by more than 75%. Wonderful, you would say. At the same time, price has decreased significantly. Wonderful, you would say. So would you say that the amount of energy that we are using to refrigerate things in our homes has decreased? Not really. What has happened? The size of our refrigerator has increased significantly. Some of us, we have only another refrigerator, we also have a freezer, or two freezers, or three freezers in the house. The price is reduced, we have a finite budget, basically we are buying more stuff for the same amount of money. So efficiency is sometimes something to be careful. Efficiency is wonderful, we're able to reduce the consumption of, but in reality what it does, you replace two other things. Let me give you another example. This is computers. Here I'm showing the amount of computation, the amount of operations that you can do with 1 kilowatt hour of power. How many operations can you do? In 1940 something, you can do in 1 kilowatt hour 1,000 operations. Now you can do 10 to the 16, 13 orders of magnitude. Wonderful, we'll reduce, the system becomes so efficient, we'll reduce 13 orders of magnitude to do a single operation. Great. At the same time, probably because of this, the price has decreased orders of magnitude. This is number for 2010, the first or second generation of the iPad. It costs about $300 or so, $400. Well, to have the same amount of power in 1940, you will need 1,000 billions of dollars. So this is how much the price has decreased. But you would imagine the computer being so efficient, the amount of energy spent in computer that will reduce from 1940 to 1999, 2015. Look at here. This is the amount of energy, percentage-wise, used by computers relative to the other uses of energy. Look at here, the beginning of course almost nothing. Here now it's about 13%. So by making things much more efficient, much more cheaply, many people use it more, therefore the net consumption really increases. So efficiency is wonderful, but has to go at the same time with a reduction of consumption that most of the times doesn't happen. So let me finish by summarizing the key elements. The summary is this: there is not real silver bullet, at least not for now. We have to do on many different fronts. Technology is one of them. Now technology is an important part of that, but you require all of them. Ultimately this being a humanistic center, no scientific center like Cervantes Center, I would say at the bottom, what really requires is change habits, which is something which is really the most difficult to think. Technology alone cannot solve the energy crisis. We need technology, but we need probably a different way of doing things. And with this non-scientific ending, let me stop here and take questions if you have any. Thank you.
Yeah,
Yes.
we'll be taking some questions. Hi, can you hear me okay? I thank you for your lecture. I was wondering, in some of like the electron scanning micrograph photos of some of the silicon wires, there was a similarity to me when I looked at it to some of fibers of they're like these carcinogenic fibers. I forget what they're called. Asbestos, right? And then also, there's an increase in the amount of, like for instance, if the superhydrophobic materials were increased, right? There'd be what would be the environmental impact on a large scale? When, you know, in the lab you're trying on a very small scale, but seeing as there's so much industrial use for this, like have we considered what the environmental impact of these
No,
surfaces?
it's a very, very good question, very valid question. The question in the essence is, what are the new challenges, environmental or health-wise, that nanotechnology can bring? Because yes, we are using a lot of materials, but a lot of material being used. This material is silicon. Silicon is being used extensively. The question is, remember what I said at the beginning, materials behave differently at the nanoscale. Is it possible the behavior of materials at the nanoscale is different from the one that we have at the major scale, at the large scale? The answer in general is yes. Even very stable materials like gold. Gold is a golden material, extremely stable, doesn't react at all. Actually, let's keep a picture there. If you look at nanoparticles of gold, they become quite reactive once they go below 4 nanometers or so. So is it possible that other materials like silicon or others will become very reactive or being different from the one that we have? Can we extrapolate the properties that we see at the large scale into the small scale? And the answer is, in general, no. So we don't take it for granted. So we assume in the laboratory that all the materials may be different, behave differently from the major scale. So we are extremely careful how to handle them until we understand properly whether they are reactive, whether they are safe or not. We are taking very, very seriously. So first is the safety of the people who are using them, and secondly, the impact on the environment. To do this, we have special filters that capture all these particles when they are not bound. Most of them are bound into the surfaces, so there's no problem. I mean, if you look at your cell phone, you have a lot of nanotechnology there, and it's very safe to you, because these are materials that absorb and embedded into a template. They are not airbound. Basically, they are not flowing. The material we are flowing, for instance, nanoparticles of something, could be carbon, could be serious, could be dangerous. So we are taking special care of those things. Please also keep in mind what I said before, nanoparticles can go anywhere. So in principle, these little tiny things of carbon nanotubes, some of you are familiar with them, can go through the membranes of the cells and can affect the cells. So these things have to be taken in. First of all, there is a significant amount of regulation. The DO has special rules regarding how to handle material because of the environmental impact, because of the safety to the operator. It's a good point. Yes?
Question?
Thank you for the talk. It's really, really interesting. Well, my question, I think, is a mandatory question nowadays. You were talking a lot about the batteries, about efficiency. So I would like to know your opinion about the battery Tesla. So does it really works? Can be the magic solution for our problems?
Right. So he's talking about a very probably about a recent announcement actually last week. Tesla announced that the big factory, somewhere in Nevada, I believe it is, right? A huge factory, and now they are promising to sell 10 kilowatt hour, is typically what average house spent per day, 10 kilowatt hour for, if I'm correct, $3,500, right? So it would be great. It would be great because you could have solar cells during the day, absorb a lot of energy, save it for the evening when it's not working, the sun is not working, or the same with the wind. It is the magic bullet we are talking about. Well, first of all, it could be for your houses, but probably not for an industrial complex. Second, you need it, of course, they are being used extensively by cars that Tesla is making. Tesla is making cars at the cost of about $100,000, can go 300 miles. So they are still in the infancy. Tesla's strategy, the way I understand it, is to create a market so that eventually you can reduce the price of all those things. The same thing is for computers. You create a technology, at the beginning it's very expensive, eventually it becomes much cheaper. Still, the question is, could it be the bullet? My answer would be no. It would be could be a partial solution, but certainly it will not be the solution. There are many other methods. The amount of energy the world requires takes away all the amount of lithium in the world. Let's not forget the lithium batteries are coming from lithium. Lithium is a mineral. You know where the big mines of lithium are? Many in China, but many in Bolivia. So Bolivia is trying to develop the industry of mining lithium oxide, to make it lithium. But again, there are many environmental aspects as well. If you look at the number, the amount of tons, or thousands or millions of tons available reserve, and see how many batteries could you produce, it's only a very tiny fraction of the amount of energy needed for the world. So it's a solution, partially, more so the cheaper it becomes, but only a partial solution. This is my opinion. Yeah.
Hi, thank you for this informative but technicals. My name is Contessa Bourbon. I'd like to ask which companies or car companies have approached or tapped the expertise of your center? And
Well,
how is the application of nanotechnology for electric cars and other renewable use for cars?
The question is, what is the connection with the kind of thing that we do with companies? I've given you a few examples. In the case of this catalyst, we are talking about Toyota and General Motors. We are also licensing some of the what we call intellectual property. We develop a number of patents associated with this material. Actually, tomorrow I will be giving a tour early in the morning for two startup companies that are interested in looking at our technologies. So for the moment, there are some big companies and also some startup companies as well. We have also collaboration with British Petroleum. British Petroleum is, as you know, it's a company, initially British, working on oil. They are very much interested in zeolite. Zeolite is a catalyst that we use in refining oil. So they are coming to our center to understand the material zeolite using some of the instrumentation that we have. We are not talking for the moment primarily with pharmaceutical companies. We are not. We are more on the energy side, on the electronic side. Any other questions?
Just to follow up, is that because you depend on funding from the Department of Energy, or is it just
Not at
because
all.
that's
Not at
how
all.
it
It's only that the kind of material. Well, the kind of material that we are more interested in are materials associated with energy. After all, our own research is funded by the Department of Energy. So the main interest is to meet the mission of the Department of Energy. We are being funded by them. They are our people, the people who fund us. We have to make sure that what we do goes back to the mission of the center. But the users who come to work with us don't have to be working on energy at all. Some of them are coming from the electronic industry, some of them are coming from the petrochemical industry, some are coming from the pharmaceutical industry. So our own internal research is mostly from energy, but the people who come to work with us are coming from many other things. I mean, I could show you in a very nice set of examples. People from MIT, for instance, are working with quantum memories, working with with nanostructure, what we call photonic crystals. They come to a laboratory to process the material to produce these quantum memories for quantum computation. So not all has to be with energy. The research that we do is primarily energy.
More questions?
I will be around for a while. I have to catch a train to go back to Long Island, and I don't want to miss it, otherwise I'm stuck here on the bench in Central Park. And I have to give a tour tomorrow at 9 o'clock in the morning. No, at 9 o'clock I have to go to the graduation ceremony of Stony Brook. At 10 o'clock I have to give the tour. So still, I better not miss my train tonight.
Can I ask a quick one?
Well, but my answer will be long.
No, that might be true. You
be
were talking one of the things that you were talking about was the water electrolysis
Yeah.
idea in order to get hydrogen. How close do you think we are from achieving that?
Very far.
Very far.
Very far. Actually, there are people who are talking about artificial photosynthesis, which were biologists in the audience. There is a particular center in California working, actually it's a consortium of many centers, it's led by Caltech, and they're working on artificial photosynthesis. There is a professor, David Nocera, who used to be at MIT, who is now at Harvard. He talks often about artificial photosynthesis. I've been listening to his talk, has not changed much in the last 8 years. It's a huge challenge. Nature knows much better than we do. We have to get even humble sometimes.
All right, so let's finish here, and we can catch Emilio during the reception. Thank you very much.